The goal of this video is basically to show you three things. 1. How to solve linear equations. 2. How to solve a formula. And 3. How you can apply a lot of this information and find the zeros of a linear function. So let's go ahead and begin. In order to solve a linear equation for a variable, basically your goal is to get that variable all alone on one side of the equal sign. Now, of course, this isn't quite an easy task. For some linear equations, you might find that there's more than one copy of the variable inside the equation. Well, for examples like these, try and get the variables together first and then isolate it on one side of the equal sign. So here below are just a few types of equations that we'll try and solve. You can see in the first example that 2x plus 3 equals 5 only has a single x. That means when I go to solve for that one, I'm basically just trying to get that x all alone. Now if you look at the one just next to it, 3 times the quantity x minus 1 equals 4x plus 5, well that actually has two copies of x in it. So if I'm going to solve that one, my first goal is actually to get those x's together and then isolate it to one side. Now what we'll find out is that sometimes you'll be dealing with an equation that doesn't look quite linear. But after a little bit of manipulation, it can turn into a linear equation. And that's the bottom example. That's x minus 3 divided by x plus 4 equals 1. Now, technically that's not quite a linear equation. But you'll see that if you multiply both sides by an x plus 4, then it's really close to a linear equation. So let's go ahead and get started and see some of the steps for solving. Now one thing you want to keep in mind is that the techniques that I'll be showing you and that we'll be working through work for linear equations. Later on when we start finding other functions that are a little bit more complicated, they'll have their own special techniques for dealing with them. But again, in this section we're just going to focus on linear equations. Now, the biggest rule that you can remember when trying to solve one of these guys is that whatever you do to one side, make sure you do it to the other side as well. And you'll see me do this tons and tons of times. So for the example that I have, 50 equals 3x plus 5, as I work to get that x all alone, I'm going to be doing the same thing on both sides of the equation over and over again until that x is completely isolated. So let's take a couple of linear equations and see if we can solve them. I'm first going to work with the one on the left. 2 times the quantity, x plus 3, is equal to 4x minus 8. Now notice in this one, I actually have two copies of x. That means our first goal is actually get those x's together and then try and isolate it on one side of the equal sign. So in order to move closer to getting them together, I'm going to distribute the 2 inside parentheses. Well, this will give us a 2x plus a 6. And on the right side, I really haven't done anything just yet, so we'll continue trying to get these x's together. Now, one way I can get them together is actually by adding or subtracting an x. And in this case, I'm going to subtract a 2x from both sides. Now notice the effect this has. When you subtract the 2x on the left, it's gone from the left. And when you subtract 2x from a 4x, you have 2x left. Now that's awesome, because when you look at it now, 6 equals 2x minus 8, we only have a single x to worry about. This means we can move on to our second goal, to get that x all alone. Alright, so in order to get it all alone, I'm going to add 8 to both sides of my equation. This will give me 14 equals 2x. Alright, it's almost isolated. Lastly, let's go ahead and divide both sides by 2 and come up with 7 is equal to x. And there you go. This is the solution to our linear equation. Now, if you're ever hesitant or you're afraid you may have made a mistake along the way, feel free to take this solution and plug it back in the original and see if it works out. If everything balances out when you plug it in, then you definitely know that you have found the solution. Alright, let's turn our attention to the example on the right. So here I have 3/4 x minus 1 equals 7/5. And again, we want to solve this one for x. Well, the good news is, with this one, I only have a single x to worry about. So I can move directly into trying to isolate it. In my first step on trying to isolate it, I'm going to add 1 to both sides. Now, in order to add 1 to 7/5, I'm going to change it to 5/5. Okay, so a slight change, but really it's the same as adding 1. Alright, I'll work with my fractions a little bit, and that'll give me 12/5 over 5. And then I have to take care of the 3/4. So I'm going to multiply both sides by 4/3. Now watch very carefully what happens on the left. When you multiply 3/4 by 4/3, you get a 1. So that isolates the x. And then on the right side, I have to show that I'm multiplying by 4/3. All right, so just a little bit of more work to do, and that's just the simplifying part. So there's an extra 3 hiding in the 12, so that'll be the same as having 4 times 4 on top, and then 5 on the bottom. So my solution for this one is 16/5. And again, if you're unsure if that's the correct answer, we'll go ahead and take 16/5, plug it in for x, and see if the equation balances out. As you can see, solving a linear equation is not that bad of a process. As long as you work to isolate that x, usually you come up with a solution. But now a quick word of warning. Be on the watch for equations that either have no solution or an infinite amount of solutions. These are very special cases. And usually when we come across the solving process, something funny happens along the way. In fact, if you're going through the solving process and you come up across a false statement, this is an indication that the equation itself has no solution. That means no matter what you try and plug in for x, it's never going to work. Now, if you go through the solving process and you come up with a true statement, well, this is an indication that there's an infinite amount of solutions that will work. Basically, you could plug in any real number for x, and the equation is always going to balance out. Well, in order to get a better idea of what I mean by a false statement and by a true statement, let's go ahead and take a look at a couple of examples. So in these two examples, one of them happens to have no solution, and one of them happens to have an infinite amount of solutions. But notice how just looking at these two equations, it's not really obvious which is which. Well, this is often the case. You won't be able to look at it and immediately tell if it has an infinite amount or no solution. It actually comes along when you're doing the solving process. So let's go ahead and try and solve these like we normally would and see what happens. Okay, so starting with the one on the left. Notice how in this one I have 2 copies of x, and so I begin with my goal of trying to get them together. Well, in order to start that, I'm going to try and distribute through the 5. All right, so this will give me a new expression. I have 4 plus 5x equals 15 plus 5x. All right, pretty good. I've gotten rid of parentheses. All right, now I continue trying to combine these x's together. Well, let's go ahead and subtract a 5x from both sides. All right, so this will leave me with 4 equals 15. Now, immediately right there, you should have a red flag that pops up in your mind. Because remember, we're trying to solve for x, and all of a sudden we don't have any more x's. All I'm left with is 4 equals 15. Now, go ahead and backtrack and make sure that I've done my steps correctly. And you'll notice that everything turned out okay. I distributed the 5 correctly, and it's okay to subtract a 5x from both sides, so I didn't make any mistakes. But sure enough, I'm left with this statement, which doesn't make any sense. 4 does not equal 15. Well, this is an example of what I call a false statement. And it's really an indication that the equation that we're dealing with does not have a solution. No matter what you try and plug in for x, it's never going to work. Well, now that that example is over, you can probably guess that the other one is my case for an infinite amount of solutions. So again, watch very carefully what happens here so that you can tell when you have an infinite amount. So in this one, again, I have 2 x's, so I'm going to try and work to get them together. Now, one of them is stuck inside a fraction. Well, in order to get a little bit closer to that fraction, I'm first going to subtract 1 from both sides. Well, this will leave me with a negative x plus 2 equals 4 minus 2x divided by 2. So I'm a little bit closer. All right, let's continue. In my next step, I'm going to multiply everything through by a number 2. So on the left side, this will give me a negative 2x plus 4. And on the right side, multiplying by 2 will cancel out that 2 in the bottom, giving me a 4 minus 2x. All right, so I'm a little bit closer on getting my x's together. Let's go ahead and add 2x to both sides. There we go. And so we're left with 4 equals 4. All right, now again, around this stage, you should have a red flag coming up in your head. We're trying to solve for x, and all of a sudden it's gone again. And furthermore, I did all of my steps correctly up to this point. But notice how the statement we're left with, 4 equals 4, actually does kind of make sense. 4 does equal 4. This is an example of a true statement, and it indicates that we could really use any real value for x, and the equation would balance out. So this is how we know we have an infinite amount of solutions. Now, if you keep in mind that whatever you do to one side, you can also do to the other, you can begin to solve formulas. Formulas are really just special equations that usually convey some sort of fundamental principle. So if you're in any type of science class, usually these come up quite a bit. Below I have several different types of formulas. One is used to relate distance and time, so distance equals rate times time. I have another one that represents the perimeter of a rectangle. It looks like I have one for simple interest. And that large one in the bottom right, that actually represents the force of gravity between two objects. So we can work to solve one of these, basically using the same tools we picked up. So imagine I start with that perimeter formula. And with this one, I want to start to solve it for L. Well, that means I just want to work until L is all alone. So I'm going to start out by subtracting a 2w from both sides. All right, looks pretty good, but L is not completely all alone yet, so I'll continue. In my next step, I'll divide everything by 2. This will give me p minus 2w divided by 2 is equal to L. And even though I'm not done with a number, I technically have solved for L. This is because it's completely all alone now. So this formula has been solved for L. Alright, let's look at one more example that's just a little bit harder. This is r times v plus q divided by w is equal to 5v. And in this one, we want to solve for v. Well, in this example, we have 2 copies of it floating around. This means our first goal is to get both v's together and then try and isolate it as best we can. Alright, so let's begin. In my first step, I'm going to try and multiply both sides by w. That's to give me a little bit better handle on the v on the left so that it is not in a fraction. So when I multiply on the left by w, that gets rid of the fraction, and you can see that it shows up on the right, 5v times w. Alright, that's a little bit better, at least I don't have fractions, but again, I need to get these guys together. So in my next step, I'm going to subtract 5vw from both sides. Well, that'll definitely get my v's to get a little bit closer together. And since the q does not have a v with it, I will subtract it from both sides as well. So it shows up on the right. So now I have r times v minus 5vw equals negative q. Alright, I still don't have my v's together, but I'm very, very close. If I factor a v out from the left, then I only have a single v. Now be careful with a step like this, because it can throw many students for a loop. Basically, when you factor it out, it's like doing the distributive property in reverse. In fact, if you start with my last step there, v times r minus 5w, and you multiply that v in there, you'll see you get the previous step. So remember to do this. It's often a handy technique to get things together. Alright, we only got one step left. Now that I have a single v, I'm going to isolate it. And since it's being multiplied by r minus 5w, that's what I'm going to divide both sides by to get it completely all alone. So after dividing both sides by r minus 5w, I get that v is equal to negative q divided by r minus 5w. And so I have solved this formula for v, since v is now completely all alone. So up to this point, I haven't said anything about functions, or how you even start to work to solve them. Well, the good news is all the techniques that I've just presented can help you find the zeros of a function. Now recall, when you're looking for the zeros of a function, you basically just want to know where that function is equal to 0. In other words, the x-intercepts. So, for example, say I had f of x was equal to 5x minus 9, and I wanted to find the zeros of that function. What I would do is I would take the 5x minus 9, I'd set it equal to 0, so essentially I have an equation now, and then I'd use the techniques that I just learned and I'd solve it. So add 9 to both sides and divide by 5, giving me that the 0 is x equals 9/5. So see, just like that. And really you can do that with many other functions as well. So if you're looking for the zeros of a function, set it equal to 0, and then solve the resulting equation.